Up until now, we've been using two compare match channels to simulate PWM, but we actually have hardware PWM support in the AVR as well. So let's have a look and see how that works. Having a look at the datasheet and looking for Fast PWM mode, we can see a timing diagram which looks remarkably similar to what we've been doing. So our timer counts gets to a top value, and we then turn our LED off when we get to the point at which we match the output compare register. And then at the bottom, we turn the timer on. Here we see a formula for calculating the frequency of the fast pulse width modulation, but let's have a look and set this up now in the registers. So we would like to use Fast PWM mode and generate the diagram as similar as possible to what we've been doing. So we want to clear output compare 1B because that's the same compare that has been clearing our LED to now. So we want to clear output compare 1B on compare match and set at the bottom. So we need to write to COM1B1 in timer counter register A. So we're just going to modify our PWM init function . And the other thing that we need to do is have a look at the timing. And we would like to use 10-bit PWM, and that means we need to write WGM12. Now notice that that's already been written to because it's common with CTC. But what we'd also like to write is WGM11 and 10, and those are also bits in timer counter register A. Okay, now what's going to happen on a compare match is that we're going to clear OC1B. What is OC1B? So let's have a look, and we see that this comes up on the diagram of the part, and you can see it's connected to pin B2. That means pin B2 as an alternate function of output compare 1B. So we want to set that as an output. Okay, we should be good to go. Let's program and have a look at the waveforms. So let's connect. Add two graphs. As before, use GPIO in pin mode. And we'll use the first graph for our LED pin, and the second for output compare 1B. Let's start, generate some data and stop. Now let's have a look at what we have. So we can see pulse width modulation gradually increasing, and then starting again from the bottom. And we'll measure a frequency just now. And the frequency is in the region of 7,700. We'll check just now if that's what we expect. So notice how the output compare channel is increasing, and then we miss 5 pulses here, well, about 5. remind you in my code what we've changed is that we're increasing in our compare vector with compare channel B, we are increasing the duty cycle 5 times. That could account for us losing these 5 pulses. Let's check the frequency here. (7813). Now let's check the formula to see if this is as expected. So in fast PWM mode, our frequency is related to the clock of the I/O over top. Recall our top is 3FF, which in hex is 1023, so our frequency should be 8 megahertz divided by 1024, which is 7812, which is almost exactly what we're measuring. And so the frequency is measured as expected.